So previously we saw that for fields of pth cohomological dimension less than or equal to 1, we could say a few things about the Brauer group and the norm group of its extensions. So naturally, our next question is which fields have pth cohomological dimension at most 1? In the previous video, we looked at the case of fields of characteristic p greater than 0. All of them have dimension, pth cohomological dimension less than or equal to 1, but we cannot apply this theorem to this case because this theorem requires that the characteristic not be p. Now in this video, we're gonna look at some more example. So why do finite fields and Lorentz series fields have pth cohomological dimension less than or equal to 1? Well, remember, how did we define the pth cohomological dimension of a field? That was defined to be the pth cohomological dimension of the absolute Galois group, right? And what is the absolute Galois group of finite fields or Lorentz series field? Well, that is just gonna be z hat. And previously, we have computed the pth cohomological dimension of z hat. Remember what that was? It is equal to 1. So the pth cohomological dimension of finite field and Lorentz series field is exactly equal to 1, and so it's less than or equal to 1, and this proposition, this theorem apply, well, unless the characteristic of the finite field is p. So now we want to look at the last case. This is a notation for the maximal unramified extension here of a complete discrete valued field with perfect residue field. Now, since we know that for field of characteristic p, the pth cohomological dimension is always less than or equal to 1, so without loss of generality, we can assume that the characteristic of k is not equal to p. Now, to show that the pth cohomological dimension of the maximal unramified extension of k is less than or equal to 1, we want to use this characterization. So we let L be a separable algebraic extension of this maximal unramified extension, and what we want to show is that the p primary part of the Brauer group of L is gonna vanish. Actually, we will show something stronger. We will show that the whole group must vanish, so that we can use the equivalence between 1 and 2 here to prove that this cohomological dimension is less than or equal to 1. Well, to do this, to prove that this is equal to 0, we need to review a little bit about central simple algebra over a complete discrete value field with perfect residue field. So the key theorem is that every central simple algebra over such a field must be split by a finite unramified extension of K. A corollary of this is that the Brauer group then, the Brauer group of the maximal unramified extension of K must vanish, must be trivial. And why is that? Well, let's say A is a central simple algebra over this maximal unramified extension. Then A can be defined over some finite unramified extension, L, of K that still lie inside K and R. This is not a completely trivial point that needs some argument, but we'll skip it for now. So now we apply the theorem for L instead of K. So A is a central simple algebra over L. So A should be split by some finite unramified extension M of L. But this M must still lie inside K and R. So then that means that A must be split over K and R, split by K and R, and so that means that the Brauer group of K and R must be trivial. So now we want to use this to show that the Brauer group of L is trivial. We might assume that L is finite over K and R, in which case, because it's separable algebraic, we can write it as K and R joining some algebraic element of the separable closure of K. Now, in light of this proposition, to show that the Brauer group of L vanishes, it suffices to show that L is the maximum unramified extension of K alpha, and this is what we'll do. Well, we lied a little bit because, as is, L is not necessarily the maximal unramified extension of K alpha. However, it will be if we add this assumption, if we assume that K alpha over K doesn't contain any non-trivial unramified subextension. Why can we make this assumption? Well, here we need to review a little bit about the theory of discrete valuation. The fact that we can make this assumption comes from the following proposition. Alright, now that we've made this assumption, why does this imply that L must be the maximal unramified extension of K alpha? Well, let's say M is another unramified extension of K alpha. Then by the previous proposition, we must have that M is equal to this. But this lies inside K and R alpha, which is L. So then L contains all the finite unramified extension of K alpha, so it must be the maximal unramified extension of K alpha.